So I just want to say thank you to Marty and any of the other organizers. It's really been exciting to be here. I'm relatively new to my professional career. I postdoc for a while, so I've only been in my current position for 3 years. So really just starting to get started on this climate change stuff in stored product insect pests. So some of you might not typically think of stored product pests as something that is susceptible to climate change because it is in these facilities or these human-made environments, but they do show a lot of seasonal variation in response to temperatures, and they occur in naturally occurring areas as well. So I'll touch on some of that and then touch on some species distribution modeling that one of our postdocs has been working on two different species. So our stored product insect pests are really wide ranging. We have some of those bark beetles that were discussed earlier. We have moths, we have weevils, we have internal feeders, we have external feeders. We have just a huge suite of insects that we have to think about when we think about these insects that get into these stored products. And one of the figures that we've been seeing recently is that to meet the demands of this growing population, cereal grains need to increase production by 70% by 2050, which is not that far away, as we all know. So we can't create new farm ground. So one of the ways we can tackle this is to protect what we've already invested in, what we've already grown. And so when this grain, which I primarily focus on, is the grain, the more durable commodities. When that comes out of the field, this estimated stock value is about $115 billion just in the United States alone. So insect-related post-harvest losses can result in about 5 to 10% of that value. So you're talking a significant loss in stored products over a yearly storage period. In developing countries such as Africa, where they don't have the structures that we have to store grain, these losses can be as high as 20 to 50%. So that's pretty significant in terms of the investment that you already put into growing these crops. So here you can see some of the damage created by some of our insects. On the left in the jars, you can see the original grain. This is wheat, and then the powder that you see on the right-hand side occurred over a 3-month period of insects infesting that. On the right-hand side, you can see a corn kernel just pretty much decimated by the larger grain borer, which I'll touch on shortly. They're an internal feeder. They lay their eggs inside the corn or inside the kernel, and then eat their way out, and their larvae kind of disperse from there. So very devastating pests in a variety of different ways. One thing we also have to deal with is the diversity of ecosystems. So we often don't think of these places as ecosystems, but they're really living and breathing, very dynamic places that these insects live. So with grain bins, we have packaged products. These are, represent seeds that are going out to farmers. And then we have these big cooperative or elevators that house tons and tons and pass through tons and tons of grain over a year. So we have these huge range of environments that we need to try to understand. So lots of challenges in this system. So Rob Morrison and I, when I started, wrote this review on kind of what we know about climate change and post-harvest systems. And we tried to highlight what we know about before harvest in the crop fields, elevated temperature, decreased moisture, elevated CO2, can have really significant impacts on your economics, your quality, your nutritional components. All of that has kind of been known and studied. But we know a lot less about what happens to these commodities when they enter the post-harvest supply chain. And so what we know in these systems is that these insects do respond to seasonal variation. So this is average Indian meal moth trap capture on a monthly basis. We monitored for a year. This is just a pet store that has not been treated with anything, no mating disruption, no insecticidal treatments. So you do see when you get to these warmer months in July and August, September, you get this spike in population in trap captures. What's really interesting is now we have to deal with this human variation because you also see this spike in December and January, which we've attributed to the influx of seasonal goods. So Christmas, you want to dress your dog up in something cute. All of that is coming in and out during that December, January period. So we've got the seasonal variation driven by temperature increases. And then you've got this human component with what products are going in and out of these environments. So Rob and I tried to really highlight what we thought might be happening with these climate change impacts, considering these buffered versus unbuffered environments. Again, it was discussed more generations. We predict to see that here. That's kind of what we're seeing when we do these laboratory tests with these insects. They reproduce faster, just like any other insect out there. We can see then the higher abundances of these sword product insects in our facilities, decreased efficacy of our IPM tactics. So we have a lot of IPM tactics that we can use right now. We see an increased importance of sanitation, and Rob has also written another really nice review on this. And then, we really just don't know what's going to happen in these environments. Are these going to be more muted relative to the unbuffered environments? Because we are decreasing that range of temperatures somewhat. So we just don't know. It left me with more questions than I had answers, and that makes for a great career, right? So as I briefly mentioned, we do have a lot of different IPM tactics right now in our toolbox. We can talk about grain chilling. So that's actually taking this chilling machine, hooking it up to your bin and blowing cold air into your stored grain. There's some biocontrol, so parasitoid wasps that we've been looking at in terms of their efficacy on these insects. Pheromones, that's huge in mating disruption and mating delay for these insects. Aeration, again, moves around the grain, blowing cold air in there, decreasing the population growth rates. Sanitation is huge because you can see these spillage situations where you just have a bunch of grain on the ground. Insects are going to find that. That's really convenient, and then they can spread to the storage areas when it does start to cool. And then fumigation and insecticidal treatments. And this is something I'm not as familiar with. I work with another researcher in our unit, but understanding how temperature changes can affect the use of fumigants and insecticides in these kind of buffered systems is going to be really crucial in the next in the future. So one way that we decided to tackle this, some of our initial questions on where we can find these insects is through species distribution modeling. And Jenica talked about this yesterday. I really laid out a nice explanation for what species distribution modeling is. So we used the type of model where you just have the presence data. Since we're not always searching for or monitoring for these insects, we decided to go with known occurrence points. And then we wanted to look at different suitability projections for the world for these insects. And then we projected to future climate scenarios as well. And I'll show who the postdoc is who worked on that, but she also wanted me to talk about or mention that there's careful consideration of establishment and interceptions. So a lot of these insects, when you're going through, shipping containers, you can see, oh, there's a interception. That's really not a case of an established population. We don't know if that insect can actually thrive in that environment. So we do careful going through our data occurrence points to kind of throw those out, as we think those are just, not really, they won't really inform on our distribution models. So again, we take the occurrence points that we have, we use some climatic variables, and then we put it into our model to optimize and consider the biology of the insect. Typically in insects, when we talk about conservation insects, like Shelby previously mentioned, these are showing shifts rather than any sort of expansion. So the movement of the center of the populations are showing this northward shift, typically when we talk about climate change. So we wanted to kind of compare that aspect to these pest species. We used a maximum entropy model with our occurrence points, and then Rachel really harnessed the use of Wallace, which uses R and the MaxEnt modeling framework, and then put that information through QGIS for some further refinement of the results. So again, here's Dr. Rachel Harmon. She's been with us for about 2 years. Her appointment is coming to an end at the end of January. So I would, if you're interested or need a new researcher at your facility, get in touch with me. She's really great. But she's been working on a variety of different insects in our system. So larger grain borer and capra beetle are the ones I'll touch on today. Larger grain borers are insects of concern in the United States. They're just on the southern border, probably into Texas already, but no documented cases. And then the capra beetle is a quarantine insect in the sort product world, so that's under high scrutiny when different shipments come in. And then lesser grain borer and the weevils, those are pretty ubiquitous, but we still wanted to get a handle on how we can understand the movement over time and in the future. So I won't touch on those today. And she's also working on some Digrotica species comparison with a group down in Missouri as well. So to briefly introduce these insects, the larger grain borer is in this Brassicaceae family, so related to the bark beetles. It's a Central American native wood boring insect, but it adapted to eating corn. It is an internal feeder, and I'm not sure what that point is. I obviously copied some slides from Rachel. So unfortunately, it was introduced to Tanzania in the late 1970s as part of a aid movement. So they brought in a whole bunch of grain during a famine, and the larger grain borer was in that grain. It has since expanded in Africa to infest cassava. So these post-harvest losses in Africa in particular can result in 40 to 70% of losses to small stakeholders. Again, I mentioned it's a species of concern for the United States, but it is a quarantine organism for many countries in the world. So here we have to start with our occurrence points. And after looking at these and knowing the history of the introduction in Africa, we did decide to separate our analyses. So we focused on Central America as the native range, and then African populations as the introduced range. So that was really trying to understand, how it entered the system and how we can better understand the distribution based on those two factors. But what we did show was that there was significant overlap in the niche space between the America populations and the Africa populations. So we did end up combining them in the end. But we did want to, make sure we understood where the differences were occurring, if there were any, between these two populations of larger grain borers. So here we have our first species distribution map. You can see the potential suitability key is on the left-hand side there with the more yellow colors, meaning higher potential suitability. So not necessarily where they are occurring, but where they could occur if they were introduced there. So we do see a significant portion of Africa, northern South America, and then a little bit into the Americas, or into North America there, in terms of highly potential suitable area. When we start to map under climate change, this is the lower projected climate change, RCP 2.6. 2050 is at the top there, and then 2070 is at the bottom. We see some expansion into different areas, kind of growing out from where we saw in this original current distribution map. So we do see some expansion into different regions, a lot on the coastal areas, we've noted, so like California starts to kind of glow more yellow in terms of highly potential area. And then under the higher RCP, the higher impact climate change, we do see some really significant suitability increases. So again, in South America here, on the coasts in Africa, and then up into California in North America as well. So again, going back to this range shifting versus expansion, what we saw in this species was definitely an expansion. So you can see the centroid points are those specific dots with the arrows on them on the maps. So those are shifting, but the biggest pattern that we see is this green is our current, and then it's expanding in the blue, and that's in 2050. And so one thing to note here is that that expansion, that blue, is really the most significant in the next, 30 years or 20-ish years. And then that additional expansion by 2070 is on the heels of that, but it's not as, significant as the really soon expansion. And this is with the 8.5 RCP as well. So then just to briefly highlight the climatic variables that are the most important to this insect, we actually found the precipitation of the coldest quarter and the minimum temperature of the coldest month. So these guys are susceptible to colder temperatures, which is something that we can try to use against them when we're talking about management plans and how to best monitor for these insects. Up next, we're going to try to add the forestry data component and some more agent-based modeling to this. As we talked about yesterday with some of these process-based models, we want to know, can it really move through the environment if it's introduced there? Does it have the right habitat to kind of establish itself in these natural or forested areas? Because once it finds a home and start products, it will do very, very well. But beyond that, we really want to understand if it can move throughout a natural space. So to move on to capra beetle, this is work in progress, but it's really exciting. And because it's our quarantine pest, we're really trying to move on this one very quickly to understand what the potential distribution is like. So this is a Trichoderma granarium. They are part of a group of dermestids. There's a bunch of dermestids and stored product insect pests, but they also diapause, as Shelby talked about just a little bit ago. So they can stay in this, dormant state for a long period of time. They stay as larvae. It's a little bit of a debate whether it's diapause or kind of an arrested development, because they will continue to eat during this time and grow bigger and bigger, which is also more potential risk to your stored products. They also can survive on pretty much anything. They don't necessarily need the grain itself. If there's been any sort of other insect infestations, they'll eat some of that leftover stuff and just really, continue to decimate over time. They were in the United States in the 1950s, but it was eradicated. Cost about $141 million in today's dollars to eradicate the capra beetle from the US. So again, this is really really searched for in shipping containers. It can lead to serious embargoes. It's really important to continue to understand the biology and distribution of this pest. So one interesting thing that we had here was we had data of the historical range again. So that's the orange data, kind of in this Northern Africa, European swath. And then we have this blue invaded range. So here you do see the points from the California infestation, and then there was some northern, northeastern points in the US, and those have been eradicated, but we still want to, they were established. So we can use those as really valuable points of information. And we did end up using all of the data to make our models. But you can see just how different a historical point only, so that's the top model or the top map there, versus all known points. You can see the difference in kind of what we know about their potential distributions with the data that you put in. So it's something that we're just kind of thinking about in terms of understanding how to best complete our data sets, how to best talk about these insects in terms of historical versus known occurrence points. So then just to very quickly highlight, this is year 2040. We used a different climate change model, scenario 585, which is the top impact climate change. And so this, again, is just a brief highlight to show that we're in trouble if the Kepler beetle ever hits America, hits, you know, down in Australia is really susceptible. And Australia is doing a really, they're doing a lot of monitoring for this insect as well. So it's already in this European area. Greece has it, our collaborators there. So it's, you know, it could be a very devastating pest if it's introduced in any of these new areas. And then here's 2060, it just increases its potential range by 2060. So we're going to hopefully do some, we just got a recent grant, so we're going to do some thermal profiling in the lab of this insect to try to add to these models to understand really what their potential distribution is and their thermal, you know, minimums and maximums. And then we're going to try to look at the risk of these different ports throughout the United States. Australia, some researchers down there have done that, and we thought that was a really cool idea to try to understand the risks and the vulnerable places in America. So some general themes, again, for sword product insects. From this species distribution model, we're seeing expansion rather than shifting. So a bigger area rather than just moving north. So not great, but that's what pests do. Adaptation capabilities, including diapods, we need to start including those in our model. We need to start including the minimums and maximums. We know some about thermal performance curves in these insects, but definitely not enough in terms of our population growth models. Again, I mentioned the human component to things. So we, you know, increased shipping of goods to make up for extreme weather events can really disperse these insects much more easily. So we, you know, climate change events that are causing, you know, devastation, wars where you need to ship in grain from around the world, you know, this can just increase the movement of these insects. So we need to be more vigilant as we continue to move forward. Extreme weather events can also cause these insects to move from these natural areas into the facilities. Behavioral adaptation is the first thing an insect's going to do. It's going to try to find a more comfy and cozy place to live and to propagate. And then agricultural economics, we all know this, that it's volatile, when to buy, when to sell, when to move your product. But this is leading to longer storage and increased shipping to different parts of the world. So some actionable steps forward. This is kind of where we're going. Like I said, I feel like I just started, but I'm already way deep into it as well. So one of the things that I came out of this meeting already is what to do next. And I'm so excited to move forward on that. There's so many established modeling frameworks that were discussed here. So trying to apply that to the sword product insects is going to be really exciting because it's kind of an untapped area of research. More predictive models, including the community ecology, so the interaction of these insects. Not a lot is known about the succession of the system, and it is a closed environment. So once that nutrition of the grain kind of gets depleted, what do these insects do in the system, and how does temperature involved with that as well in the nutritional depletion? We've been working really hard on automated detection that will help our timely treatments. We use a lot of different sensors, volatile sensors, image detection. So we're really trying to combine our engineering and our entomology and attack it that way. Like I said, continuous monitoring throughout the US and world. I'm on year 3 of a North-South Great Plains monitoring project. So I have a lot of great collaborators from North or Canada down through Oklahoma that have been collecting samples once a week for 3 years. I don't know how I convinced them to do that, but that's been pretty crazy. So hopefully do some forecasting and look at the phenology of the insects over time, at least in those 3 years and maybe longer. Develop some remediation plans, especially for the capra beetle and the larger grain borer. So it was discussed yesterday. We're going to find them eventually, and we can't be slow on our response. So we need to understand what's going to work, how it's going to work with different temperatures, and how we can just continue to like be ready for these insects. I have a graduate student that is looking at the lesser grain borer movement from natural landscapes into facilities, in particular on overwintering, and understanding how they're using behavioral adaptations for that. And then I've been trying to get into this with social science impacts. So I'm part of the translational working group with the Ecological Forecasting Initiative. And so we talk a lot about how do we bring these models into the hands of users that will actually use them and understand them and make decisions based on them as well. So with that, I have my whole group to thank. And again, thank you for inviting me. This has been really great.
Questions for Alison?
So I'm really interested in the idea of movement of species from natural communities to stored grains and potentially vice versa. So do you have any data that tells you that happens?
No. Mostly we just stick with these interception traps. So that was part of this 3 years of data on a more local level. We have ground traps and we have hanging traps, and then we have probe traps in the bulk grain. And so we do see a lot of overlap in the communities just within that area. So that's about the only like scale that I can comment on. We just submitted a grant to look at that on a more broad scale, from like field to the storage, and then at different spatial scales. So cross your fingers for us.
Glenn, you have a question online?
Yeah, I guess Brittany Barker would be the one to ask this question. She's our species distribution model expert. But we ran into problems with publications being refused because these correlative approaches like Maxent are not considered to be valid for forecasts. Did that come up, or has that controversy been solved? Or what did Rachel do to mitigate that problem?
Yeah, that hasn't come up for us at all in terms of using it to project based on these like known climate change scenarios. We haven't done any like very, population specific growth forecasting. We haven't done any of that with Maxent. We'd probably use more of a machine learning based algorithm for that in R. But yeah, for the species distribution models, we haven't had hardly any pushback in terms of projecting the climate change.
Yeah, that's odd because 10 years ago, a lot of journals wouldn't publish your work. I think what's happening, my theory is that so many people are just submitting so much using these correlative approaches that people just gave up protesting, or somebody solved the problem by saying, oh, they're actually pretty good at forecasts. But it used to be you could have your article refused for publication by the editors. And one thing Brittany did was use 5 different correlative models and run tests to see how valid, or cross-validation tests to see how they compare. And I would also add that among those 5 different approaches, she would get very different results from some of them. And that's evidence that you shouldn't use them for forecasting. Anyway, that's my soapbox for the day, I guess.
I think that's a really good point to consider too. And what we've noticed too, since getting into this space, is there is a lot of junk that is trying to get published right now using this MaxEnt stuff. And it is really sad. And it's such a shame because it is a good modeling system, but people aren't even optimizing their models. They're not doing any sort of correlation in their bioclimatic variables. They're just inserting their occurrence points and making maps. And they're not even discussing, yeah, anyway, yes, I have a soapbox too.
It is kind of a cookie cutter push buttons thing that any student can throw the data in there and push the button and not know what it means or what the pitfalls are. So yeah,
Yeah, it can be dangerous, but yeah.
thanks.
I'll just add to that, since I've also published a bunch of these models doing forecasting, right, is you do actually need to be thinking critically about how you're validating your models, right? Like, if you are just feeding your data in and pushing the button and accepting all of the defaults of this R package or software, then yeah, garbage in, garbage out is true of any modeling framework you could come up with. So simply because they're correlative models, like a linear regression is a correlative model, right? Like that doesn't demonize them as an approach, but it does behoove us to be thoughtful about how we're constructing our models, how we're optimizing them. You have to understand all of the tuning knobs in MaxEnt or any other modeling method do, and know that they're set appropriately for the species you're working